I'm Guy O'Lakin. I'm the teacher. And this is statics. Today we're going to start out by going through the syllabus, talking about the class a little bit, and then we'll have time to get into the material too. As we're going through the syllabus, feel free to ask questions, ask me to clarify anything. Okay. So first, I know a lot of people here are from Normandale, but I think there's a lot of people who normally go to school at other places. So you need to get used to D2L. That's how I'm going to get materials to you through this class. And the way to get to D2L is go to the Normandale website. It says D2L up at the top. Click on that and enter your login and password. If you can't figure out how to get that working, if you have trouble with that, there's tech support. I can point you to them. They can probably help you better than I can, but I'd be happy to try to help you. So if you log in, you get something like this. With a list of your classes on the right side, and this is statics. So go in there, and when you get into statics on D2L, it's going to give you a list of all the little announcements that I've made. It's just going to be sequential. So there's one here right now that says welcome to statics, blah blah blah. The syllabus is posted, and all the posted materials are going to be under materials and then content. So I'll show you how to get there. And then usually after class, after I know what we've covered, I'll go back and tell you which problems are assigned, and I'll post that in the news. Today, you can do these problems without, no matter how much we cover, so this is the assignment. So I'll show you how to find that stuff. Okay, so all of the things, the documents that I give you are going to be under materials and then content. And the content is broken up into categories on the left. Course information is where the syllabus is. Then there's also vector review. That's just a text document you can read in order to do the vector problems that are the first assignment, today's assignment. There's code for some programs for a TI-89 calculator that'll be helpful in this class. Writing your own programs for those TI calculators. I think most of you probably have TI calculators, and it's so nice to have for equations and calculations that you do over and over again, to just have them programmed in there so you don't have to type things over and over again. We're going to do a lot of vector calculations, and we're going to do some matrix calculations. And so as much as possible, you'd like to not have to type those in value after value. We'll be dealing with 2x2 and 3x3 matrices and 2-element and 3-element vectors. So if you can streamline the process of typing in all those values over and over again, it can be nice. And then there's some stuff that's going to come up later on, a list of all the centroids in 2 dimensions, reaction loads in 2 dimensions and 3 dimensions. I have 2D twice because I think when I put this document on here, I couldn't figure out how to break up the PDF. But anyways, hopefully they don't disagree with each other, the two. That would be a drag. Then, after course information, there are the assignments. And so these are all the problems for the class right here, broken up into categories. The ones that you have to do today are the vector problems. Most of the time you won't do a whole set of problems in a single day. They'll be spread over a couple of classes. But each of these, like if you click on vectors, those are the problems for today. And then let's go to a later one. Okay, so here's one that these problems, some of them are a little complicated. We won't do all those in one day, but I think there's a total of 77 problems, and this class is about those 77 problems, trying to help you understand these problems really well. And if you get to the point where you understand these 77 problems really well, how to do them, you could explain how to do them to somebody, then you'll do great in the class. What else is on here? Oh, and then there's solutions to all of these. The solutions are already posted. On every set of assignment problems, there's 1, 2, or 3 problems that don't have solutions posted, and I'll post those solutions after you hand in these assignments. But for the majority of these problems, like you're being assigned these problems and the solutions are there. So if you get stuck, you can look at the solution. As much as possible, the way you want to do these is work on them without looking at the solutions, and then just go to the solution for a hint when you get stuck, okay? Or to compare your final answer once you get through it. Okay, so let's go through the syllabus. This is 3 credits. It's taught over 5 weeks, which means that, so to think about the workload and the credits, and I think this is an important thing that everybody needs to be sort of clear on, like what's the requirement for this summer class? How much other stuff can you do when you're taking a 3-credit summer class? During a normal semester, you take your 3-credit class spread out over 17 weeks. Okay, we're doing it over 5 weeks, which means that this 3-credit class during these 5 weeks is about the workload equivalent of 10.2 credits. Okay, so think about it that way. You're taking, for the next 5 weeks, you're taking a 10.2 semester credit workload. You know what I'm talking about? So if you're thinking of taking, so I know people talk to me about, taking 2 classes at once. It's possible. Some people can do it, but you're talking about the equivalent of taking over 20 credits at the same time for a 5-week chunk of a semester. You know what I mean? That's most people. For most people, I would recommend that you don't do that. And even for the small number of people who can get through that, my recommendation tends to be just take one of the classes and learn it better. You know what I mean? If you know all the stuff in each of your basic engineering classes really well, it's going to carry you really nicely through your later classes. I think it's a good idea to try to solidify this stuff as much as you can. And sometimes I know everybody wants to get through and it costs money and blah, 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 but as much as you can slow yourself down and concentrate on just learning these classes well, I think it'll pay off in the long run. Okay, and so workload, day-to-day workload. So we have class 2 hours a day, 5 days a week. The general guidelines for any college class, and you could Google this and you'd see the same answer for every university. It's recommended that you spend 2 hours outside of class for every 1 hour you spend in lecture. What did I say, 2 hours? 2 to 3 hours, actually. For this class, I think 2 hours will do it, but that means still that you have 10 hours of lecture a week. You should be spending 20 hours on this material outside of lecture every week. Okay, so that's a 30-hour-a-week commitment, and for some people possibly more. 30 to 40 hours a week is the way it would break down according to the guidelines that universities give you. So you don't want to spend a ton of time working. Again, there are people who could work full time and take a class like this, but not that many people. And even for the people who can, I would suggest that that's not in your best interest. Spend the extra time learning the material. That's what I would recommend. Okay, so 30 hours a week is about what you should expect to spend on this class. It's about the equivalent of 10 credits during a full semester. That's sort of the way to think about it. Anyone have any questions about that? Okay. The class time is 1 to 3 in this room. You found it. It's the other people I need to be telling that to. Office hours are Monday through Thursday from 3 to 4. So no office hours on Friday. But hopefully you'll find that's enough time. And the way we're going to do office hours is, I don't know what labs are open from 3 to 4, but we're going to find one of the labs down the hall that's open, and we're just going to do it sort of like study hall. So if you have the time, I would recommend just getting in the habit of, after class ends at 3, wander down to the lab that we're in, start working on your material. Other students will be in there to work with. I'll be in there to help if you have questions. Okay. Prerequisites are Physics 1 and Calc 2. And it says there's a co-requisite of differential equations. That's a very soft co-requisite. You could do perfectly fine in this class without being in differential equations. That's just the same co-requisite they have at the U of Minnesota, so that's how we have it. There's actually, this is a very light calculus class. It's mainly just a class about free body diagrams, figuring out what forces are applied by joints, that kind of thing. It doesn't have much to do with calculus. The materials that you need for this class, you need a good calculator, a graphing calculator. If you don't have one yet, I would recommend, if you're in the market for a calculator, be sure you get one that does eigenvalues and eigenvectors. It'll serve you well as you go on in engineering. Basically, every class you're in from now on, you're going to have to compute eigenvalues and eigenvectors. In this one, actually, I think this one we don't do that, but it's about the last one where we won't talk about eigenvalues. And there are some things here where it could come up. We just don't talk about it that way. Reference books. There is no required textbook of any kind. The lecture is just totally self-contained. I do think it's a good idea to have a reference book as you move on after this class, and so there's 2 recommendations. One is the textbook that they use at the U, Beer, Johnson, and Mazurek. And you can use any edition of that. Basically, they're all the same, except they just change the problems around to try to make you spend more money each semester. And then Sham's Outlines for Engineering. I don't know how many of you have ever seen Sham's Outlines, but it's like the greatest book series ever. I would recommend getting a Sham's Outline for every single class you take. They cost like $15 or $20, and they're just loaded with problems, with solutions. So like if you're trying to get ready for like the fundamentals of engineering exam or something, it's just all the kind of problems that you need to be doing to get ready for that. So that's what I would recommend as a reference book. Okay, there's no textbook for this class, which means that everything you need to know is going to be in your notes. One thing that'll help you with that possibly is the way I'm doing this lecture right now. So I'm gonna be doing my lectures like this is the whiteboard, you know, and as I'm doing that, I'm recording a video of what I'm doing. So you can go back later on D2L. I'll post videos of, you'll see the pen moving around, you'll see what I'm writing, and you'll hear my voice. So you can rewatch any lectures that you miss or anything that you want to see again, went by too fast or whatever. And I'll also post PDFs of all the stuff that I write. So especially if you miss a day, that'll be useful. Or if your notes are hard to read for a day or multiple days or whatever, after the class is over, you can always just print out the PDFs. But that's your textbook for the class, just the lecture. It cuts down, I think, compared to most classes, a lot of classes, it cuts down drastically on the amount of material that you're expected to be responsible for. When you think about a textbook where you're covering 200 pages or something, we're talking about you're responsible each day for maybe 8 handwritten pages. That's not very much material. But the trade-off is I'm doing that to cut down on the amount of material that you have to have in your head. And the trade-off to me is I expect you to remember everything that I said. I expect you to read those notes over again like it's a small textbook assignment. And I don't think it's too much to ask to basically, somewhat just remember everything that I say. You should be reading back over your notes the same way you read a textbook assignment. Okay. All right. So now the next parts of the syllabus are just talking about the topics that we're going to cover, course objectives. None of that is, let's skip all that. You can look back at that later, but I don't think any of that means too much right now. Okay, so let's talk about the grading scale, how the grade is broken down. The grading scale is most likely going to be a straight scale. That's how it almost always ends up being in my classes. It's pretty rare that I ever have to do any curving or anything. The A's are 92 and above. The B's are 82 to 92, and then 70, 60. Compared to some classes you've taken, that scale might seem kind of high, especially the 92 and 82. People grumble about that. But to me, I think of it this way. I try to make this class just about the things that I consider to be absolutely essential that you understand well. And then I think, to get an A, you basically should understand all those topics perfectly, And as an engineer, that makes a lot more sense to me than giving tests where people getting 55% or getting A's or something, Like, I can't think of anything more important as an engineer than understanding what you know, what you don't know, the stuff that you do know, it cold. That seems like the way to approach it. So I don't know. I know there are professors who disagree with me on that, but I don't understand why. That total grade is broken down this way. 60% tests, 20% assignments that you hand in, and 20% assignment quizzes. And so I'll go into detail on what each of those are. Does anyone have any questions about the grading approach yet?
Just out of curiosity, historically, how many students in your class do you get a year?
I'd say at least as many as any other class you've been in. I don't think I grade particularly hard or anything.
Do I have a quiz tomorrow?
Quiz, I think you have an assignment. Let me look at the schedule. I think the deal, you have an assignment that's, we're supposed to have a quiz today, but we're not going to have that. But we do have an assignment. Oh, wait. Oh, today's Tuesday, right. So let's not have a quiz tomorrow. That seems a little extreme.
So it's going to be Thursday then?
So I don't know. We'll get to that. Let's sort of follow the. Okay, so first exams. There are going to be 4 exams. Well, there's going to be an exam every Friday, so that's easy to remember. So each of those exams is going to be cumulative up to that point. Each of those is worth 15% of your grade. 4 exam scores go into your grade, and wait, what? I guess that's. Does that make sense? So yeah, that's the idea. I might have to think about that. But so the idea is the first 4 Fridays of the class, there's going to be an exam for the whole class. It's worth 15% of your grade. If you miss any one of those, or if you just score badly on one of those and you wish you hadn't, maybe some people maybe like scoring badly on tests, but for the people who, then the next Friday there's going to be a cumulative final that you can use as a makeup for any one of those first 4. So if you miss exam 2, I'm not going to give a makeup for exam 2 like the day after or anything like that. It'll stay as 0 until the end of the semester when you'll take this cumulative final at the end, and that you can use to make up exam 2. And if you don't miss any exams, you can use that to make up your worst score over the semester. Yep?
So then theoretically then, if you're satisfied with your first 4 scores in the first 4 exams, you can opt out of the final?
That's right. That's what I'm sort of second guessing the timing of this here, because that means that you're missing a whole week of class in a 5-week class. I better think about that and revisit. But
you don't have to if you don't want to.
Yeah. I think we might have to. Boy, I'll have to think about that. I'll think about that, and we're gonna. So we might have to move exam 4, to later. That's true, yeah. That's true. Okay, yes, you're right. Let me think about it. And after I think about it, I'm going to come up with the perfect solution. Everybody's going to be happy with it. All right. Now the assignments are going to be collected every Tuesday and Thursday, not today. And I'll give you a daily assignment after every class. What I'm going to do when I collect these assignments, I just don't have time to grade every problem that I assign. So I'm going to look at it to make sure that you've basically you've worked on all the problems. And then I'm going to use a random number generator. You can just get those online. Just go online and it'll spit out a random number for you. So I'm going to use that to determine 1 or 2 problems that I'm going to grade carefully. So it's a statistical sampling thing. And so you can sort of do it, you can think of it a little bit like a lottery. If you don't always know how to do all the problems, or you don't do every problem carefully, then some weeks you're going to get lucky, and I'll grade the ones that you have done carefully. Some weeks you're going to be unlucky and be like, oh, I knew how to do all the other ones, and then I ended up picking the one that you didn't do. And the idea is that in the long run, the people who are careful about every problem end up with a higher score. There's a couple things I want to say about assignments. The first one is engineering. I think of this as a professional degree, and I expect your work to, different people, that means different things to different instructors. Like, I don't care what you wear to class, well, to a degree. But to quite an extreme degree, I don't care what you wear, I don't care how bad you smell, anything like that. But I do want you to turn in assignments that look nice and neat and are legible and easy to read, because that's an important habit to get into. And so if you turn in work that looks sloppy, or it's hard to read, or it's hard to follow, like a page is scribbled out and, an arrow goes here to the, I'm going to take points off for that, because I think that's a bad habit to get into in your engineering classes. So I just expect you to turn in work that looks neat, okay, and is easy for me to read. Also, I encourage you to work together with others. The cutoff to me between working together and copying someone else's work is after you work together, you should go off by yourself and be able to write up the solution that you hand in to me without looking at your notes or consulting another person or anything like that. Like, at some point, the knowledge that you gain from working together with your classmates needs to be in your own brain. Okay, that's the distinction to me. If that's hazy to you, come talk to me and maybe we can clear it up. I don't think that's probably going to be too much of a problem, since most of the questions I give you have solutions posted already anyways. But there are some that the solutions aren't posted, and it might be helpful to work together for those. Any questions about any of that? Yes? Yes. Oh, yeah, to make it, yes, sure. Yeah, pencils are fine. Any kind of paper is fine. I don't care about that stuff. Just make your writing, and especially your figures, look neat, and make sure that the train of thought is such that I can follow it. Yep.
The assignments you showed on the board, are we supposed to print those out and write on those, or just write on?
On other paper. I don't think there'll be enough room on those. But I think what you probably want to do is, especially if you're using like a 3-hole binder, just print out all those problems, put it in your binder, and then you can refer back to them later. And then besides the assignments, there are also assignment quizzes on Mondays and Wednesdays. And the assignment quizzes are going to cover 2 things. One, they're going to be short answer questions about what did I say here, what did I say the 3 key facts you need to remember are about, stuff that I said in lecture. So you need to be reading the lecture notes. Okay. The second thing that's going to be on the assignment quizzes are problems that were in, so always a lecture quiz will be, okay, so the assignment quiz is also going to cover the problems that were in the previous assignment that you turned in. Okay, so you have to do those problems for the assignment to hand in, and then I'll give them back, hopefully the next day. And then you need to be able to reproduce those problems on the quiz. The quiz is just going to be like 1 question, 1 or 2 short answer questions. It's going to take 15 minutes or something. But that's the idea. Any questions about that?
Is there some kind of makeup quiz?
Makeup quizzes, well, let's see. So how many quizzes are there going to be total? I hadn't really thought about makeup quizzes. So there's going to be 10 total quizzes worth 20% of your grade, so 2% each. So I think let's try it with no makeup quizzes, you know what I mean, since it's only 2% of your grade. Who has a strong reaction to that?
We'll see at the end of the class.
Yeah. Yeah, right, exactly.
The emphasis is on lectures, correct? So just being here for lectures.
For the quizzes?
For pretty much everything, it sounds like everything you're providing is going to be lecture-based.
Yeah, everything is just based on the lectures. Yep. There's nothing else but the lectures. So, and actually, so I said that I recommend having a reference book for later on to go back and refer to. But actually, my recommendation while the class is going on is not to use anything else. I think, based on my experience, I think the best advice I can give you is just do everything you can to understand what I said. If you don't understand something, ask me about it. Outside sources are going to do things differently, and so I feel like my lectures are just directly intended to guide you towards being able to do these 77 problems, and the easiest way to be able to do them is to focus on the lectures and leave the books for later. Okay. Any questions about assignment quizzes? Yep.
Sorry, about
Oh,
assignments?
yes.
Will you accept like emailed assignments or things like that?
Oh yeah, maybe email is hard for me, but why don't I'll make drop boxes on D2L, so it's the same thing. You'll just submit it to D2L. It's no harder for you. One thing that I would like with any electronic submissions of assignments is like the hardest thing to deal with is submissions of a set of like pictures of, you know, like someone will turn in a 5-page assignment as 5 separate JPEGs, and then some or all of them are upside down, most likely, or whatever. So if you want to submit things electronically, please figure out how to submit a single assignment as a single PDF. Okay, just a single file. But as long as you do that, yeah, I'd be happy to take electronic submissions. Question? No. Any other questions? All right. And then a thing that says don't cheat. So mostly that could come up, the most likely way that could come up is copying on an exam or a quiz. And it says what I'll do if that happens. I don't usually have trouble with that in engineering classes. I've had trouble with that more often in like basic physics, like college physics classes and stuff. So, but in case you were wondering, like, I wonder if he wants us to cheat or not. It didn't. So that's why that's here. Like, no, I'd prefer if you did not. Okay, any questions about the class or the syllabus? That's it. All right, so the first thing that we have to, before we get into the vector review, let me just talk a little bit about what statics is, what kind of stuff we're going to be learning. So you can think of statics as the first course in mechanics. And mechanics essentially is broken up into figuring out will an object break, and how will the object move. So mechanics is a whole area of study. You can kind of break it down in this way. If statics is the starting point, you branch off in one direction to mechanics of materials, which is what we call deform at this school, because that's what they call it at the U, but almost every other university in the country calls it mechanics of materials. And then going in the other direction, so this is a class that talks about, what if I color-coded these? Well, next semester. Dang. So this is the side that has to do with will the object break, and there's obviously some overlap in these different sides. And then the other direction is dynamics. And that has to do with how will the object move. And after you take mechanics of materials, you basically go into a whole sequence of, like, now you do intermediate mechanics of materials, advanced mechanics of materials, continuum mechanics. So I'm going to write that one in case you ever hear that in, like cocktail conversation or whatever, and you can just be like, but isn't continuum mechanics just really a branch of, whatever? You can act like a genius. Making people think you're smart is an important part of being an engineer. Okay, so continuum mechanics. And then let's say, so continuum mechanics is a fully mathematical approach to the bending and breaking of objects. A really more practical approach, the approach that's always used in industry, that's usually used in research, is finite element analysis. That's a numerical approach to the same kind of things. People call that FEA or FEM for finite element method. And from dynamics, you go to for those of you who are in aerospace, going into aerospace engineering or mechanical engineering, I think you'll take an intermediate dynamics class like your junior year. And then it'll break up into Lagrangian dynamics, where you're using energy methods, and Newtonian, let's say advanced Newtonian mechanics, where you're talking about forces. Okay. So that's kind of a summary of what's coming up in, and what didn't I say? I didn't say fluid mechanics. That would come out of here too. Fluid dynamics. Okay, so those are kind of the topics that are coming up on the horizon for any of you who are doing mechanical engineering, aerospace engineering. Some of these, for the people doing civil engineering, you'll do some of these same things, but some things will be different. Here are some examples of calculations we'll be able to do after we're done with a class in statics. So the first one, let's say, and this is actually a problem that in one of the later assignment sets. So say you got this thing. It's called a rangeur, like, sounds French. And it looks like kind of a double pliers set. They use it in medical applications. That sounds very painful. you apply a force here, and there's something here, often a bone, unfortunately. And if you apply a force F to the handles here, the question is, what's the force applied to the bone? So that has to do with structures, combinations of rigid bodies connected by joints. And we'll be able to do problems like this by the end of this class. Another application of structures. And this is one that I like because my research was all in biomechanics related stuff. Is imagine, so this is a diver who has thin thighs, thin calves. Nice butt, though. Okay, so he's getting ready to dive off of the platform. He looks confident. Look at his legs. That does not look healthy. So the question is, what's the tension in his Achilles tendon right now? And really, that's just another application of a structures problem. We're going to treat the foot, the lower leg, the upper leg, the pelvis, the spine, the arm, all of these as individual rigid bodies connected by joints. We're going to treat the muscles and tendons as cables connecting the different rigid bodies. And then based on what we know about equilibrium, we're going to use that to calculate the forces that have to be applied to keep this system at rest. Then something else that we'll be able to do, so imagine this is a bike frame. I don't know if I can draw this 3D very well, but let's try. Okay, and then there'd be one more bar there. Okay, so you'll just have to take my word for it. That's a bike frame. And let's say that there's a force F1 applied here, a force F2 applied here. Say that these are forces that you could measure, occur in riding whatever kind of terrain this bike is designed for. There's a force here, F4, something else here, F2, something else here. Okay, you get the idea. So you've measured that these are the forces that are going to be applied to this bike in whatever application it's made for. Where in this frame, where is the frame at the greatest risk for fracture? So obviously bike companies spend a lot of time and money on analyses like this. The analyses that they do go into the calculations that you start talking about in D-form. But just from using statics, we can figure out a lot of the important information that goes into this kind of analysis. So this is kind of the world of calculations that we're going to go into in this class. So now let's talk about the equations that we're going to see in statics. For general rigid bodies, the equations of motion are Newton's second law and the rotational version of Newton's second law. Newton's second law, I always write that N2L just to save time. And that equation says the sum of all the forces, or I'll write it as the net force acting on a chosen body, is equal to the mass of the chosen body times the acceleration of the body's center of mass. So that's the first equation. And then the second one is the rotational version of Newton's second law, the moment equation. I'll always just abbreviate this Rn2L. And this one's a little more complicated. The form looks similar, though. You've all seen this in Physics 1. The sum of the moments produced by all the forces about some point A is equal to the moment of inertia about A, and that's actually a matrix, times the angular acceleration of the body. That's a vector. And we're not even done with this yet. That A cannot be anything. Your choices are limited. That A, your about point, has to be either the body's center of mass or a point that's fixed to the ground, like connected by a ball and socket joint or a hinge or something like that. So this is what you have to deal with in dynamics. It's much easier in statics. Because in all the cases that we're going to deal with, the acceleration of the center of mass and the angular acceleration are equal to 0. 0 vectors. So for us, our first equation is Newton's second law, and it says that the net force is equal to 0. And the rotational version of Newton's second law says that the sum of the moments about a point A are equal to 0. And now, since the rotational version of Newton's second law holds any time that A is fixed in your inertial coordinate system, this holds for any point that we're dealing with, because for a body that's at rest in a coordinate system, something that's static, every point in the coordinate system is fixed in the body and in the coordinate system. So this holds for any point A. And that's exciting news. as physics goes. You'll see when you do dynamics that these restrictions on what you can use as your about point is a really big deal that we have to consider in every problem we do. In statics, we never have to consider that. Choose any point you want as the about point. This means that statics problems rarely turn into differential equations. Let's say they rarely introduce differential equations. And the reason that you don't get differential equations because of these zeros on the right-hand side is that the way differential equations come up in dynamics usually is that the acceleration of the center of mass is the second time derivative of the position of the center of mass, and the angular acceleration of the body is the second time derivative of the angular position of the body, and so it naturally leads to differential equations. Here, that stuff's all gone away, and so we're not going to have to deal with that. And that's the biggest reason why dynamics is very calc-heavy and statics is not. Anybody have any questions about, so that's sort of where we're going with this stuff. All of this means that, so the purpose of doing a class in statics then, I think partly it's some skills that you need to have later, and sometimes as an engineer you have to do statics calculations. But I think the bigger thing is it allows us, so Newton's second law and the rotational Newton's second law have a lot of stuff going on. They have loads acting on the left side of the equation. They have motions happening on the right side of the equation. And early on, you have a lot to learn about both of those two things. By starting out in statics, it gives us the luxury of focusing on the loads, working on free body diagrams, figuring out how to separate forces up, separate couples and moments up, without having to worry about the messiness of the differential equations. So this is basically, it ends up being a class on getting really good at free body diagrams and recognizing how connections between bodies introduce forces and moments to other surrounding bodies. All right. So let's do class like this pretty much every day. We'll do about an hour. We'll take a 10-minute break, come back, and do the second hour. So let's take a break right now. Come back I'll start again at 2:05, and we'll start the vector review.